Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
A peculiar form of intellectual chaos began to permeate the world of computation in the early 1960s. The machines themselves, hulking mainframes housed in climate-controlled rooms, were monuments to deterministic logic. Their operations, governed by the crisp physics of vacuum tubes and magnetic cause, were predictable and absolute. Concurrently, the instructions fed into them were becoming profoundly elaborate. The ambition of programmers had begun to outpace the expressive power of their tools. For the first time, humanity was attempting to construct artifacts of pure information on a scale previously unimaginable, and the blueprints were failing. The challenge was most acute in the realm of simulation, the ambitious attempt to mirror complex, real-world systems within the machine's memory. Scientists and engineers sought to model the intricate dance of neutrons in a reactor core, the logistical ballet of a shipping fleet, or the unpredictable flow of customers through a service system. The programs written to capture these realities grew into monstrous, labyrinthine structures. They were vast, monolithic scripts, often thousands of lines long, where the flow of control would leap wildly from one section to another through a tangled web of go-to statements. Data was stored in global variables, accessible and modifiable from anywhere within the program, creating a cascade of unforeseen dependencies. A change in one routine could have baffling and catastrophic effects on a completely unrelated part of the code. Debugging such a system resembled a form of technological exorcism, a desperate search for the logical ghost in the machine. This phenomenon, later christened the software crisis, was a testament to a fundamental mismatch. The sequential, top-to-bottom logic of prevailing programming languages was proving profoundly inadequate for describing systems characterized by multiple, concurrent, and interacting agents. The code formed a chaotic scroll known as spaghetti, a technical term that captured the unstructured mess. Within this environment of burgeoning complexity stood the Norwegian Computing Center, the NCC, in Oslo. Established in 1952, it was a practical institution, a place where the abstract power of computation was brought to bear on the concrete problems of Norwegian industry and research. Its clients were concerned with operational research, with optimizing shipping routes, managing industrial processes, and understanding physical phenomena. The NCC served as a crucible, applying the formal elegance of mathematics to the messy, probabilistic realities of the world. The demand was for working simulations that produced reliable results, and the existing tools were beginning to buckle under the strain. Into this setting stepped a young mathematician named Ole-Johan Dahl. Having completed his studies in numerical analysis at the University of Oslo, Dahl joined the NCC in 1962. He was, by all accounts, a quiet, deeply thoughtful man, possessing a mind that craved precision and logical coherence. His background was in the formal, structured world of mathematics, a domain where axioms lead to theorems with irrefutable certainty. He entered the sprawling, ad hoc craft of large-scale programming. His initial mandate was direct and pragmatic, to assist in the development of simulation programs. The tool of choice at the NCC was ALGOL-60. ALGOL, an acronym for Algorithmic Language, was itself a major intellectual achievement. It was a creation of an international committee of computer scientists and mathematicians who sought to design a universal language for describing algorithms. ALGOL presented a model of theoretical purity. It introduced the concept of block structure, allowing programmers to group statements and their associated data into self-contained units. It supported recursion, the ability of a procedure to call itself, which opened up elegant solutions to a whole class of problems. Its syntax was specified with a formal grammar, a level of rigor that was itself a landmark in computer science. For the academic community, ALGOL-60 was a thing of beauty, a language that reflected the structured thinking of mathematics. The specific tasks facing Dahl and his colleagues revealed a deep-seated limitation within this elegant structure. ALGOL, like all major languages of its era, conceptualized a program as a single, unified chain of command. The computer would execute one instruction, then the next, following a solitary path through the code. This model was perfectly suited for calculating a mathematical formula or sorting a list of numbers. This model presented significant challenges for modeling a system like a supermarket with its many customers, each with their own shopping list and path, interacting with multiple cashiers, each with their own pace and queue. To force such a multifaceted reality into a single, sequential narrative required immense contortion. Programmers had to manually manage all the interacting parts, keeping track of each customer's state, scheduling their next action in a complex event list, and painstakingly ensuring that the simulation's clock advanced in a coherent way. The language provided the primitive building blocks of arithmetic and logic, which left the entire architectural burden of the simulation on the programmer. Dahl's initial response was characteristically pragmatic and grounded in the tools at hand. He began by working within the confines of ALGOL, developing a series of sophisticated procedures and library extensions to ease the burden. He and his colleagues created powerful routines for managing the crucial components of a simulation: event schedulers to handle the timing of actions, random number generators to introduce statistical variation, and data collection tools to analyze the results. This was an exercise in building a higher level of abstraction on top of the language's primitive foundation. These ALGOL extensions were clever and effective, and they made the development of complex simulations more manageable. They were, in essence, a way of taming the spaghetti, of imposing a degree of order on the inherent chaos by packaging common patterns into reusable components. This success simultaneously illuminated a more profound issue: the work of creating these libraries, of wrestling the sequential nature of ALGOL into a form that could mimic a world of parallel activity, revealed the core of the problem. The difficulty was rooted in the language's fundamental worldview. A conceptual dissonance arose between the simulationist's worldview, which saw a collection of active, interacting objects, each possessing its own properties and behavior, and the programming language's model, which offered a single, omniscient actor executing a monolithic script. The bridge between the conceptual model of the problem and the conceptual model of the tool was weak and required an enormous amount of intellectual scaffolding to maintain. The constant effort to manage this conceptual gap was the very source of the overwhelming complexity. These powerful extensions, functioning as patches, ultimately highlighted the paradigm's fundamental inadequacy. A solution lay somewhere deeper, in a fundamental rethinking of what a program could be and how it could describe the world. This profound recognition of the conceptual dissonance set the stage for a period of intense intellectual creation. The challenge was immense to forge a new linguistic tool, a vocabulary for computation that could faithfully articulate a world teeming with concurrent activities. The existing languages, for all their algorithmic power, were monologues delivered by a single, tireless calculator. Dahl and Nygaard sought to create a language capable of staging a drama, of orchestrating a chorus of interacting agents, each with its own story to tell. This required developing a paradigm for process description, aiming for a form of computational expression where the program's structure would become a direct, intuitive map of the system it illuminated. The specific problems driving this inquiry came from the burgeoning field of operations research. Consider the deceptively simple scenario of a port, with ships arriving, waiting for a berth, unloading cargo, and departing, or a nuclear reactor where countless neutrons are born, travel through various materials, cause fissions, and are eventually absorbed. In each case, the system is composed of numerous entities or processes that exist simultaneously and whose life cycles unfold in parallel. A ship's existence continues while it waits. A neutron's journey progresses independently of others. To model this with a language like Fortran was an exercise in heroic bookkeeping. The programmer was forced to manually manage the state of every single entity, to painstakingly advance a global clock in discrete steps, and at each step, to iterate through every entity to see if it was due for a change in status. The program's logic became a sprawling, monolithic control loop, a structure whose form diverged from the distributed, agent-based reality of the port or the reactor. The complexity was explosive, and the resulting code was brittle and profoundly difficult to reason about. The breakthrough, emerging from the collaboration between Dahl and Nygaard at the Norwegian Computing Center, was the concept of the process. This was a revolutionary linguistic construct. A process, in their formulation, was a unified entity encapsulating its own data attributes and its own sequence of actions. Consider a ship process. Its data includes its arrival time, cargo type, and required unloading duration. Its sequence of actions constitutes its life story, which involves arriving at the port, requesting a berth, waiting if necessary, occupying the berth, unloading, releasing the berth, and departing. A radical innovation was assigning the sequence of actions its own private instruction counter, a form of local sequence control. This design meant a process could execute a portion of its life story, pause itself, and yield control to a master scheduler. Later, when conditions were appropriate, it could be reactivated to resume its actions precisely where it had left off. This capability for suspension and resumption formed the core of the solution. It allowed a single computer processor to interleave the execution of many process life cycles, which created a faithful illusion of parallel existence. This mechanism, known today as a coroutine, became the engine that powered discrete event simulation. The language itself would manage the event queue, a timeline of all scheduled future events. When a ship process was created, it could schedule its own arrival at a specific future time. The simulation would then advance the clock to that moment, activate the ship, and allow it to run its script. If the ship required a berth that was currently occupied, its script would instruct it to enter a waiting state and become passive. It would cede control, and the scheduler would awaken the next process on the event list. When another process, such as the berth itself, finished its task and became free, it could then reactivate the first waiting ship, which would resume its life story from the exact point of interruption. This powerful idea was formalized in a language they called Simula, later known as Simula 1, completed around 1964. To maintain a sense of familiarity and to leverage a robust existing foundation, they designed it as a superset of the elegant and widespread language ALGOL 60. The design provided programmers with the familiar features of ALGOL alongside a new set of primitives for process-based modeling. A programmer could write a process declaration, which served as a blueprint for a certain kind of entity, like customer or neutron. From this blueprint, the program could generate any number of individual process objects, each with its own data and its own independent life cycle running within the simulation's temporal framework. The language provided commands like hold to make a process pause for a certain duration of simulated time and passivate to enter an indefinite waiting state. It also provided mechanisms for processes to reference and interact with one another, forming queues and other dynamic relationships. The effect on the practice of simulation was immediate and transformative, replacing the tortuous, centralized control loops of Fortran with decentralized, object-like descriptions. The code began to read like a description of the system itself. One could define a core process in a traffic light process, and the program's structure would reflect their real-world interactions. The conceptual gap that had plagued earlier efforts was effectively closed. The mental model of the simulationist and the formal structure of the programming language were at last aligned. This alignment produced programs that were vastly more modular, readable, and scalable. Complex systems that were previously intractable could now be modeled with a newfound clarity and confidence. Simula achieved the creation of a computational paradigm that was both specialized and profoundly insightful. Its worldview was entirely oriented around the concept of simulated time and the sequencing of events. The language's architecture, with its implicit central scheduler, was tailored for this domain. It provided a brilliant solution to a specific, challenging class of problems. Within this specialized tool lay the seed of a greater revolution. The core concept of a process, an active entity bundling data with its own operational rules, possessed a power and a generality applicable to domains outside discrete event simulation. The journey of Dahl and Nygaard continued, elevating this powerful idea from a tool for modeling the world toward a tool for building it. A profound insight, once articulated, often reveals itself as the key to a much larger intellectual landscape. For Ole-Johan Dahl and his collaborator Kristen Nygaard, the process concept within Simula was such an insight. It had solved the immediate and complex problem of system simulation with remarkable elegance. The power of their creation fostered a sense of intellectual unease and a recognition of its untapped potential. The process was a brilliant actor performing on the highly specialized stage of discrete event simulation, a world governed by the inexorable ticking of a central clock. The question percolating to their discussions was whether this actor could be freed from its stage, and whether this powerful method for describing simulated entities could become a universal method for describing reality in all its computational forms. This challenge defined the transition from Simula to its world-changing successor. The problem was one of abstraction and generalization. Within Simula, a process was an inseparable fusion of data and action, an entity like a car at an intersection or a customer in a queue, whose behavior was defined by a sequence of operations unfolding over simulated time. Its identity was tied to the simulation's master scheduler, the mechanism that would suspend and resume its operation, weaving its story into the larger narrative of the system. This tight coupling provided descriptive power for modeling and simultaneously imposed a fundamental limitation for general-purpose computing. Dahl and Nygaard perceived that the essence of their idea, a self-contained unit encapsulating state and behavior, could be applied to almost any concept a programmer might wish to represent. A geometric figure on a screen, a record in a database, a component of a user interface, or an abstract mathematical theorem could all be conceived as such units. The task was to find a formal mechanism to liberate this concept from the specifics of simulation. The intellectual breakthrough, a moment of profound conceptual clarity primarily attributed to Dahl's genius for formal language design, was the act of cleaving the process into two distinct yet related ideas. The first was the idea of a blueprint, a formal description of a category of things. This blueprint would define the common structure and the potential behaviors for all entities of that type. The second was the idea of an instance, a concrete manifestation generated from that blueprint with its own unique existence and state. This act of conceptual fission was the birth of the class and the object. The class was the template, the abstract definition. The object was the living, breathing entity created from that template, a specific instance in the memory of the machine. With this new class construct, Dahl architected a way to describe the world in terms of concepts. A programmer could now define a class named point, specifying that it contains two data attributes, an x-coordinate and a y-coordinate, along with procedures to move it or calculate its distance from another point. From this single class definition, one could then generate thousands of distinct point objects, each with its own specific location, all sharing the same fundamental structure and capabilities. The process of Simula was reborn as a general-purpose mechanism for creating user-defined data types of arbitrary complexity. This creation of the class was accompanied by a second, equally critical, act of liberation, the decoupling of the object from the simulation's timekeeping mechanism. An object, once created from its class, became a sovereign entity within the program, operating as an active agent whose behaviors or methods could be invoked directly by any other part of the program at any time. This transformation elevated the concept into an active agent for any computational environment. The language itself was reframed into a framework enabling a dynamic society of interacting, autonomous agents, which replaced the model of a single, sequential story orchestrated by a master narrator. This conceptual evolution culminated in the creation of a new language, Simula 67. The name itself signifies the deep continuity with its predecessor, while the change in its fundamental architecture represented a revolution. Simula 67 was a true general-purpose programming language that retained the powerful simulation features of Simula, presenting them as a specific application of a much grander idea. The core of the language was a class and object. The entire philosophy of programming was being inverted. The prevailing procedural paradigm, exemplified by languages like Fortran and Algol, viewed the world as a collection of data upon which a set of procedures acted. Dahl and Nygaard's work with Simula 67 offered a radically different ontology. In their new vision, the program's universe was populated by objects. These objects were the primary actors. They encapsulated their own data and the procedures that operated on that data, shielding their internal complexity from the outside world. A program's execution was the emergent behavior arising from the messages passed between these objects as they requested services and information from one another. This profound philosophical shift placed its conceptual emphasis on the object, the concept, the thing itself. It was a way of structuring software that mirrored the way humans often structure their understanding of the world, as a system of interacting entities with the inherent properties and behaviors. Dahl's meticulous work on the syntax, the semantics, and the compiler implementation ensured that this powerful philosophical vision was grounded in a robust and practical engineering reality. The invention of the class construct in Simula 67 was the single most important step in the formalization of what we now call object-oriented programming. It provided the foundational building block, the atom of this new computational worldview. It was an act of generalization of the highest order, taking a specific, powerful solution and abstracting its essence into a universal principle. By creating this mechanism, Dahl and Nygaard had given programmers a tool for building more modular, more understandable, and more extensible software systems. They had laid the cornerstone for a new way of thinking about computation. Establishing this cornerstone immediately revealed the next layer of the architectural challenge: the ability to define concepts like the class point, the class circle, and the class square as distinct entities raised a new and compelling question. These concepts are clearly related, as a circle and a square are specific kinds of geometric shapes. The challenge became expressing this conceptual hierarchy within a programming language. This required defining a general class for shape, and then specifying that the class circle and the class square were specialized versions of it, sharing some properties, while adding their own unique characteristics. The creation of the class concept resolved one issue and consequently eliminated the deeper problem of classification, specialization, and shared identity. The stage was set for the next revolutionary steps in their intellectual journey. The monumental achievement of the intellectual framework for the class concept immediately presented its creators with a more profound and subtle challenge. The ability to encapsulate data and behavior into discrete objects was akin to an anatomist learning to identify individual organs. The next logical step for achieving deep understanding was taxonomy, the science of classification and relationship. The programming world of the 1960s possessed tools for reuse, including subroutine libraries for sharing common functions and the pervasive practice of manual code replication. These methods were conceptually limited, leaving a need for a way to capture the essential hierarchical nature of reality that Dahl and Nygaard sought to model. For example, a truck object and a car object are both types of a vehicle object. They share fundamental properties like an engine, wheels, and a capacity for movement, alongside possessing distinct specializations. A language defining the class truck and the class car as completely separate entities compelled the programmer to manually duplicate their shared vehicular DNA, revealing a significant conceptual limitation. The challenge involved expressing and as a kind of relationship, a cornerstone of human thought, within the rigid syntax of a programming language. Dahl and Nygaard's solution to this dilemma was a breathtakingly elegant and powerful mechanism of inheritance, actualized and similar through the subclass declaration. This was a formal linguistic tool that allowed a programmer to define a new class as an extension of an existing one. A class designated as a subclass of another, its superclass, would automatically possess all the data attributes and procedural capabilities of its parent. The conceptual breakthrough was immense. Code reuse was transformed from an mundane act of copying into a sophisticated act of conceptual specialization. Consider a general class named geometric figure. It might contain data for its position on a plane, for example, integer coordinates x and y, and a procedure to reposition it. By declaring a new class named circle as a subclass of geometric figure, the circle class immediately gained the x and y coordinates and the reposition procedure. The programmer was then free to add attributes specific to a circle, such as a radius, and procedures unique to it, such as calculate area. This hierarchical structure offered profound benefits for correctness and maintainability. If a more efficient way to represent coordinates was discovered, the change could be made a single time in the geometric figure superclass. Every subclass, including circle, square, and triangle, would instantly inherit the improvement. This mechanism mirrored the very structure of knowledge itself. It allowed programmers to build from the general to the specific, creating rich taxonomies of concepts directly within the code. The program became a model of a domain of knowledge with explicit relationships of ancestry and specialization. This method created a structured and interconnected world, a significant evolution from the design of earlier procedural languages. Dahl and Nygaard had provided a way to build libraries of concepts, a way to reason about software systems in terms of their underlying structure and interconnections. This powerful structuring principle of inheritance, however, created a new and equally compelling operational question. If one has a collection of objects belonging to this new hierarchical family, for instance a list of geometric figures containing a mix of circle and square objects, how does one write code to interact with them? How could a program, for example, instruct every figure in the list to draw itself on the screen? The conventional procedural approach presented significant maintenance challenges. It would demand a chain of conditional checks, such as if the current object is of type circle, then invoke the draw circle function, and if it is of type square, invoke the draw square function. This solution possessed a fundamental limitation. The introduction of a new shape, perhaps a pentagon, would necessitate finding and modifying every single one of these conditional blocks throughout the entire program, a process prone to errors and escalating complexity. The answer to this operational puzzle was the second pillar of Dahl and Nygaard's new paradigm, polymorphism, enabled through the brilliant concept of the virtual procedure. This idea provided a dynamic operational principle that worked in concert with a static structure of inheritance. A procedure could be declared as virtual within a superclass. This declaration served as a contract, a placeholder for behavior that all its descendants were expected to exhibit, each in its own way. The geometric figure class could declare a virtual procedure draw. The circle subclass would provide its concrete implementation of draw, containing the specific logic for rendering a circle, and the square subclass would provide its implementation with the logic for drawing a square. The true genius of this design revealed itself in its execution. A piece of code could now iterate through the list of geometric figures and, for each one, call the draw procedure. The Simula runtime system, at the moment of the call, would perform a remarkable feat. It would inspect the true type of the object in question, for example, a circle or a square, and automatically dispatch the call to the correct, specialized draw implementation. This mechanism, now known as dynamic dispatch or late binding, was revolutionary. The client code that initiated the drawing operation remained wonderfully abstract. It operated on the general concept of a geometric figure and its contractual obligation to be drawable. Its operation was confined to this general concept, independent of the specific geometric forms being manipulated. This decoupling was a radical liberation. Programmers could write general, robust algorithms that worked on an entire family of related objects, confident that the system would handle those specific behaviors correctly. One could add the pentagon class with its own draw procedure, and the original drawing loop would accommodate it automatically, its own code remaining unchanged. Inheritance and polymorphism functioned as a single, powerful conceptual unit. Inheritance structured and shared code through conceptual hierarchies, and polymorphism enabled flexible, extensible, and abstract operations upon them. Together, they formed the very engine of object-oriented programming. Their influence is difficult to overstate. Every significant software system developed in the modern era, from operating system graphical user interfaces to complex scientific simulations and vast enterprise applications, relies on these foundational principles. The architectural patterns that define high-quality software design today are, in essence, sophisticated elaborations of the core ideas of class, hierarchies, and polymorphic behavior first articulated in Simula 67. Dahl and Nygaard's work yielded a programming language and a formal system for modeling complex realities, a framework for thought that would permanently alter the intellectual landscape of computation. The practicalities of getting this revolutionary paradigm adopted by a world comfortable with its existing tools, however, would prove to be an entirely different sort of challenge. The intellectual triumph of Simula 67, with its elegant synthesis of data and behavior, entered a computing world defined by its own unique imperatives. The landscape of the late 1960s and early 1970s was a realm of scarce resources. Memory was measured in kilobytes, processor cycles were precious commodities, and the dominant programming languages were forged in the crucible of efficiency above all else. Fortran, the undisputed titan of scientific and engineering computation, was designed to translate mathematical formulas into the fastest possible machine instructions. COBOL, its counterpart in the business world, was optimized for the massive data file processing required by mainframe systems. These languages were lean, direct, and powerful tools for their specific domains. They treated the computer as a machine to be commanded with maximum economy. Simula entered this environment as a creature from another conceptual plane. Its power lay in abstraction, in the dynamic creation and management of objects, and in the flexible dispatch of polymorphic methods. These features, the source of the language's expressive force, also incurred a performance cost on contemporary hardware. Instantiating a new object required the complex operation of dynamic memory allocation from a heap. The system also needed a mechanism for automatic garbage collection to reclaim the memory of expired objects. To a programmer meticulously managing every byte in a common block, this background process appeared as an extravagant and unpredictable consumption of valuable machine time. The polymorphism enabled by virtual methods introduced a layer of runtime interaction. When a program called a method on an object, the system had to perform a lookup in a virtual table to find the correct version of the code to execute. This introduced a minuscule delay. Procedural languages employed direct, hardwired function calls where the destination of every call was known at compile time. In an era where programmers counted machine cycles, Simula's architectural beauty was paired with a perception of metabolic slowness. The paradigm asked for an investment in structural integrity and long-term maintainability. The contemporary market overwhelmingly rewarded immediate, raw performance. The conceptual gulf was equally vast. The object-oriented model required a programmer to decompose a problem into a society of interacting agents, each encapsulating its own state and logic. This represented a profound cognitive change. The prevailing procedural model viewed a program as a monolithic sequence of instructions operating on a passive, global pool of data. The benefits of Simula's approach, including code reuse through inheritance, safer systems through encapsulation, and adaptability through polymorphism, were long-term architectural advantages. The promise of cleaner, more robust, and more scalable systems existed alongside the pressing concerns of most software development shops. which involved meeting immediate deadlines and optimizing for constrained hardware. Simula offered a vocabulary for designing cathedrals to an audience primarily engaged in the rapid construction of functional workshops. Consequently, the language found its home within academic institutions and advanced research laboratories. In these environments, its conceptual power was appreciated, with a primary focus on its modeling capabilities. As a revered instrument for research and a tool for teaching advanced programming concepts, it occupied a position on the periphery of mainstream commercial software development. This commercial quietude afforded Ole-Johan Dahl the intellectual space to pursue the logical extension of his life's work. The creation of Simula was an effort to manage the immense complexity of software systems by imposing a coherent structure upon them. Having developed a powerful way to organize programs, Dahl turned his attention to an even more fundamental challenge, establishing the correctness of their behavior. This inquiry led deep into the burgeoning field of formal methods, a discipline dedicated to using mathematical logic to specify and verify the properties of computer programs. The central problem was one of certainty. The conventional method for finding errors, software testing, was an empirical process. It could demonstrate the presence of bugs by executing a program with a sample of inputs, leaving the possibility of undiscovered errors. For any program of meaningful complexity, the effectively infinite space of possible inputs precludes exhaustive testing. Dahl, alongside other luminaries of the era like Stroustrup and CVR, sought a path toward absolute confidence. They envisioned a world where a program's correctness could be proven with the same rigor as a mathematical theorem. The intellectual toolkit for this endeavor was formal logic, specifically axiomatic systems for reasoning about program execution. Dahl's work in this area focused heavily on ideas related to Hoare logic. This framework provides a way to annotate programs with logical assertions. A precondition is a statement that must be true before a segment of code is executed. A postcondition is a statement that must be true after it finishes. The goal is to prove, mathematically, that if the precondition holds, the execution of the code guarantees that the postcondition will hold. This transforms programming from an empirical craft into a deductive science. Dahl's unique contribution was to connect these ideas of formal verification directly to the principles of structured programming, which were themselves foundational to the class-based structure of Simula. In the highly influential monograph Hierarchical Program Structures, co-authored with Stroustrup and Hoare, he helped articulate a powerful synthesis. The argument was that the ability to reason formally about a program is inextricably linked to the clarity of its structure. Programs constructed from simple, well-understood, and verifiable components, loops, conditional statements, and procedure calls were themselves more amenable to formal proof. A complex system built from provably correct modules could inherit that correctness. This philosophy mirrored the object-oriented vision of building complex software from self-contained, reliable objects. It revealed a deep consistency in Dahl's intellectual trajectory, a persistent quest for the principles that allow humanity to master computational complexity, first through architectural structure with Simula, and then through logical certainty with formal methods. He was building the intellectual scaffolding for a future of truly reliable software engineering. The intellectual pursuit of mastering complexity, which had led Dahl toward the logical certainties of formal methods, found its most world-altering expression through a different form of propagation. As a commercial product, the Simula language achieved modest adoption within specialized European academic and research circles. Its ultimate destiny was to serve as a powerful intellectual catalyst. The concepts embedded within its architecture possessed a generative potency, allowing them to flourish widely and influence development outside its immediate user base. Simula's triumph lies in its ideas taking root in other minds and other places, inspiring the creation of languages that would define the modern computational landscape. This transmission occurred along two primary and profoundly influential vectors, fueled by both a quest for philosophical purity and an urgent need for pragmatic power. The first of these vectors originated with a pilgrimage of thoughts undertaken by a young, visionary researcher from the University of Utah named Alan Kay. In the late 1960s, Kay was thinking with a fertile blend of molecular biology, mathematics, and the nascent field of computer graphics, was already formulating radical ideas about a future of personal, dynamic computing, a concept he would later christen the Diener book. He envisioned a world where computation was accessible, malleable, and empowering for everyone, especially children. His challenge was finding a software paradigm equal to this grand vision. The procedural, top-down programming models of the era presented a challenge, feeling as restrictive as trying to describe a vibrant, living ecosystem with a rigid language of a military command structure. His encounter with Simula 67, during a visit to Oslo, was the moment of intellectual crystallization. Looking at Dahl and Nygaard's creation, Kay perceived a profound new principle underlying its programming language features. He saw a new metaphor for computation itself. The Simula object, a self-contained entity bundling data, and the procedures that operated on that data, struck him with the force of revelation. He saw it as a virtual computer, a software analog to a biological cell. Each object possessed its own state and its own behavior, communicating with other objects through a well-defined interface of messages. This was a key. The complexity of a large system could be managed by composing these autonomous, reliable components, each responsible for its own internal world. Returning to the United States and joining the now legendary Xerox Palo Alto Research Center, or Park carried the seed of an idea and cultivated it in one of history's most fertile intellectual environments. The result was Smalltalk. If Simula was the book of Genesis for object-oriented programming, Smalltalk was its gospel. Kay and his team, including Dan Ingalls and Adele Goldberg, took the Simula concept and amplified it to its philosophical zenith. In Smalltalk, everything became an object, from numbers and characters to windows and processes. The entire system was a universe of objects passing messages to one another. This was a profound and elegant unification. The programming environment itself was built using the very principles it espoused, creating a seamless, reflective world where the user could inspect, modify, and extend any part of the system. Smalltalk represented the Platonic ideal of the object-oriented paradigm, a pure expression of the architectural principles first articulated in Simula, and it would become the intellectual wellspring for graphical user interfaces, the Apple Macintosh, and generations of dynamic programming languages. While Kay was pursuing this path of philosophical purity on the West Coast, the second great vector of Simula's influence was taking shape within the deeply pragmatic engineering culture of Bell Telephone Laboratories in New Jersey. There, a Danish computer scientist named Bjarne Stroustrup confronted another set of equally challenging problems. For his doctoral work at Cambridge, Stroustrup had implemented a large-scale simulator for a distributed computing system. The language he chose for the task was Simula. He developed a deep appreciation for its expressive power. The class construct provided a unique elegance and clarity for modeling his complex systems components. Concurrently, as the simulation grew, he encountered practical limitations when the program's execution became prohibitively slow. This necessitated a rewrite of the entire project in a lower-level language for the final version. The process was tedious and error-prone, sacrificing the carefully crafted, elegant structure for performance. This experience left an indelible mark on him. Upon joining Bell Labs in 1979, he was tasked with analyzing the Unix kernel for distributed computing applications. He found himself facing the same dilemma. The dominant language for systems programming was C, a language renowned for its efficiency, its portability, and its intimate relationship with the underlying hardware. It was fast and powerful. For large projects, it presented a landscape of pointers, data structures, and functions that required programmers to manually enforce high-level organization. Stroustrup wanted the modeling power of Simula combined with the performance of C. He needed a tool that offered abstraction and preserved runtime efficiency. His solution was a masterstroke of pragmatic synthesis. He embarked on a project to extend the C language with Simula-like features. His initial creation, aptly named C with classes, introduced the core Dahl and Nygaard's invention directly into the heart of the world's most successful systems programming language. He added the class with its bundling of data and methods, constructors, destructors, and the concept of inheritance. This hybrid approach proved to be a Trojan horse for object-oriented programming. It offered a gentle migration path for the vast global community of C programmers. They could gradually adopt these new features to better structure their programs, to build reusable components, and to manage complexity, all while preserving their existing codebases and the performance characteristics they depended on. C with classes evolved, gaining virtual functions, templates, and a host of other features, eventually becoming the language C++. Its industrial strength combination of abstraction and efficiency propelled object-oriented programming from an academic curiosity into the dominant paradigm for commercial software development for decades. Through Stroustrup's work, the DNA of Simula was spliced directly into the workhorse of the software industry, ensuring its principles would shape everything from operating systems and databases to video games and financial trading platforms. The decades-long intellectual current that flowed from a small computing center in Oslo, carving new channels through academic research and eventually irrigating the vast landscape of commercial software, reached its formal apex in 2001 in a ceremony that represented the entire field's acknowledgement of a fundamental shift. The Association for Computing Machinery bestowed upon Ole-Johan Dahl and Kristen Nygaard its highest honor, the Turing Award. The citation was a model of potent brevity, recognizing them for ideas fundamental to the emergence of object-oriented programming. It was a crowning moment of recognition for a lifetime of intellectual partnership, a validation of concepts that had once seemed esoteric and were now the bedrock of a global industry. The award, poignant in its timing coming the year before Dahl's passing, served as the world's definitive statement on the magnitude of their achievement. This ultimate accolade, however, points toward a profound epistemological contribution. The legacy of Ole-Johan Dahl represents a revolution in the very way human beings conceptualize and structure solutions to complex problems using a computer. His work provided a new worldview, a coherent and powerful mental framework for translating the messy, interconnected, and dynamic reality of a system into the rigorous and logical domain of code. He helped to architect a fundamental change in the relationship between the programmer's mind and the machine's operation. The prevailing procedural mindset of the early computer age conceived of a program as a recipe. This approach involved a central, omniscient processor executing a prescribed sequence of commands upon a passive collection of data. Intellectual power was concentrated within the algorithm, the verb treating the data, the known, as inert matter for manipulation. This approach proved powerful for well-defined mathematical and scientific calculations. Its limitations emerged when modeling intricate real-world systems with many interacting parts, such as shipyard operations, traffic flow, or biological processes. The complexity of managing the state of thousands of variables and their tangled interdependencies created a cognitive barrier, revealing the strain on procedural programming. Dahl and Nygaard's work, culminating in Simula, offered a radically different ontology for the computational universe. Their world was populated by active, self-contained entities, objects, each possessing its own state and its own repertoire of behaviors. A program became a simulated reality, a society of interacting agents communicating and collaborating to produce an emergent, system-level outcome. This was a profound decentralization of control. The intelligence of the system was distributed among the objects themselves, each responsible for its own integrity. This conceptual model, a world composed of autonomous things, provided a natural fit for the problems they sought to solve. It enabled the software's structure to mirror the problem domain's structure directly. This conceptual framework succeeded with such immense force because it resonates deeply with how the human mind naturally organizes reality. We perceive the world as being full of objects. We categorize them into classes based on shared properties and behaviors. A car represents a class of objects, and a specific vehicle is an instance of that class possessing its own unique state, including its color, its mileage, and its current velocity. We understand that all cars share certain behaviors, like accelerating and braking. We also build mental hierarchies. A sports car and a delivery truck are both specialized types of cars, inheriting common attributes while adding their own unique features. Dahl and Nygaard's great insight was to formalize these intuitive cognitive strategies of classification, encapsulation, and inheritance, and embed them in a programming language. They forged a bridge between the analog, pattern-matching way humans perceive complex systems and the discrete, logical world of the digital computer. The true measure of Ole-Johan Dahl's legacy, therefore, is discovered in the cognitive clarity he bestowed upon generations of software architects. He equipped them with their vocabulary and a grammar to tame the immense complexity that procedural methods struggled to contain. The principles he helped pioneer became the foundation for structured design, enabling the creation of vast, sophisticated software systems that could be built, maintained, and extended over time by large teams of engineers. The concept of the reusable component, a self-contained object that can be plugged into countless different systems, is a direct descendant of the Simula class. The entire modern discipline of software engineering, with its emphasis on modularity, abstraction, and managing dependencies, is an ongoing dialogue with the ideas first articulated by Dahl and Nygaard. His later work on formal methods and program verification with colleagues like Tony Hoare reveals the depth of his commitment to intellectual rigor. He sought a way to reason about the correctness of these complex object-oriented systems with mathematical precision. This pursuit of provably correct software, of building programs that were as reliable as they were elegant, shows a mind constantly pushing toward a deeper understanding of the fundamental principles of computation. He was a builder of concepts and a verifier of their soundness, a rare combination of the visionary architect and the master craftsman. Every elegant software architecture, every robust application programming interface, every system that successfully models a piece of our intricate world stands as a quiet monument to the profound and enduring vision forged in the quiet halls of the Norwegian Computing Center. The foundational ideas remain, persisting through the evolution of languages, the exponential growth of hardware power, and the expansion of ambition beyond what anyone in the 1960s could have imagined. They persist because they are powerful, they are effective, and they align with the very structure of human thought. Ole-Johan Dahl's provision of a new programming language fundamentally altered how programmers see.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.